she is well known for her work on STPA and STAMP that helps in accident analysis. She has authored 2 books, and I believe there are other books on the way. And she's member of NAE, so it's a great honor for us to have her as a guest speaker today. And with that, Nancy, I will let you take over. And if I missed some details that you feel important, please feel free to say.
Okay, so let me see if I can get.
Oh, you should be able to screen share, right?
I don't use Teams very often.
The share button is on the top right.
Share content. I think this will work.
Thank you.
It's just a little slow. Oh, come on. You can't see anything, I guess, right?
We see your screen, but
oh, your screen. Oh.
If you open your presentation, we will see it.
Okay.
Then now we see your slides. You just have to go into slideshow mode.
Okay, yeah. Let me get the slideshow. There we go. All right. So I'm not going to give a really technical presentation today. What I really want to explain is why a new approach is really necessary, and just the outline of what a new approach means to safety engineering. I started this. I did normal things as a graduate student. Like everyone else in computer science, I did a dissertation on formal methods. But then my dissertation was plagiarized, and immediately, and I was bored with the topic anyway, and I had just arrived at my first teaching position, and I got a call from someone at an aerospace company that said they were building this torpedo, and this was 1980. And they said, we're not so concerned the torpedo misses the other guy, but we are concerned that it turns around 180 degrees and hits us. And there's all these computers on this torpedo, and we've never had computers like this on a torpedo, and we're really concerned about it. And so we'd like you to help us with software safety. And I said, well, I don't know anything about that. You know, I do formal methods, I do beautiful math, and formal logic. And so they said, well, no, well, we called everyone else in your department, and they've all said no to us. And I said, well, I'm sorry, you know, I don't know anything about torpedoes. And they said, well, we have some money. So I said, well, let me put Professor Leveson on the phone. She's the torpedo expert. Anyway, I finally did accept it. It was for 6 months. I thought, well, I'll learn something about torpedoes, and while I'm deciding what else I want to do. And this is the torpedo. This is called ADCAP. And you can see it coming out of the torpedo tube up on the upper right there. And it, let me get a pointer. And so I didn't help them much. I had absolutely no idea how. I didn't help them at all, I don't think, but it wasn't a lot of money either. And after 6 months, they called me and they said, well, are you interested in what happened? And I said, sure. And they said, well, we took this torpedo out off the coast of California to the torpedo proving grounds, and the Navy owns this part of the ocean. And we fired it, and every time we fired it, it came out of the tube, it turned itself off, it laid down on the bottom, and it just sort of lay there. And I said, well, it's safe. And they said, well, the Navy doesn't want to pay for this safe torpedo. So I said, well, what did you do about it? And they said, well, one by one, we took off safety devices until we got it safe enough and reliable enough. And it was the first time it really hit me that safety and reliability were different things. I decided, well, I'll spend, this doesn't seem like a good strategy, build the whole thing and then take things off. So I'll spend 6 months and I'll look at this problem and solve it and then go on back to my math, my formal logic. And then, but I've still worked on it, but it took me a little bit of time, 30 years, but I finally figured out, I think, the solution to it. So let me tell you a little bit more about this problem. And in industry, they have a really nice thing of doing what they call the bottom line up front. The conclusions first and then the details in the talk. So here are my conclusions, and then I'll fill in the details later. The problem is the complexity is reaching a new level. It's really a tipping point. The old safety approaches are becoming less effective, and losses are being caused by new things, especially related to the loss to the use of software and autonomy. And the traditional approaches just don't provide the information necessary to prevent losses in these systems. So I believe that we need a paradigm change to a systems approach based on systems theory, which changes the focus from reliability and preventing failures to enforcing safe behavior. And what this does for you, this paradigm change allows you to do things we just couldn't do before. The analysis techniques are much more powerful, inclusive. It turns out they're orders of magnitude less expensive, which really surprised me. It works on extremely complex systems. This is being now used on the most complex systems that are being built in the world today. Most of those are, many of them are defense systems that are really complex, but it's also being used on more common types of systems. And one of the things that we discovered is that we could design safety, security, and other properties in the system from the beginning instead of trying to add them on later, because it's so expensive. If you build something and then you find you built the wrong thing and you have to go back and change it, it's almost prohibitively expensive. And of course, the question is, does it work? And it turns out that we've done a lot of controlled studies, I'll mention this later, and empirical evaluations, hundreds. And it finds more of the causal scenarios, the unknown unknowns that engineers call it. And it can be used before a detailed design exists, as I said. Okay, so that's what you're going to hear. Let me fill in the details now about what this is. First, we have to start with a general definition of safety, and we define it much more generally than other people. We add more things, we can do more things. So an accident, or as in the Defense Department, it's called a mishap, is any undesired and unplanned event that results in some loss. That could be a loss of human life and injury, or injury, which is the normal definition of safety. Property damage, also pretty normal. Environmental pollution, mission loss, loss of protected information, negative business impact, like damage to one's reputation, and so on. So it's a very, very broad definition, and it includes both. I said undesired and unplanned, but it didn't say whether it was intentional or not. And so security is also included, and we haven't done a whole lot on security until relatively recently, but we're doing a lot more now. And the problem is that if you see here, this is a timeline, and after World War II, we started building much more complex and technology intensive systems. And FMEA, of course, was for integrated circuits at the end of World War II or around there. And there were a lot of tools that came up: fault tree analysis, event tree analysis. HAZOP is something in the chemical industry in the 60s. And there was an assumption at that time that accidents are caused by component failures, including human errors. Um, and they worked. I mean, it not surprising everybody uses those things because they worked at that time. The problem is around the late 70s, and I got my ADCAP thing around 1980, we started introducing computer controls. Computers were used, but just for computation, not for control. And the use of computers allowed exponential increases in complexity, where we're adding new technology into these systems. The roles of humans started to change in the systems. And these old techniques that everybody used started becoming less effective. STPAR thing was around 2004, I think I wrote my first paper on it. And the problem is that this assumption about way the accidents are caused has changed because we have new causes of accidents occurring. The traditional approach to safety engineering was to assume that accidents are caused by failures, and then all of our reliability and safety engineering analysis tools depend on those, and those are all just various kinds of tools. And what you do is basically evaluate the reliability of each component separately and later combine these analysis results into some kind of system reliability value. There was an assumption and then the safety and reliability were really the same thing, or the reliability of the components. And that these failures were independent, that they were random. And then it turns out that humans and software don't behave that way. Once they did this analysis, they did design, and all the things that you're used to, and you'll probably all been taught in engineering school, redundancy, barriers to prevent failure propaganda, high propagation, high component integrity, over design, add in margins, safety margins, fail-safe design. And for humans, they provided operational procedures, checklists, training, and so on. Okay, so that's really what safety engineering, and until we came along, pretty much what safety engineering was, and still lots of people trying to do this. Let me show you an example of a real accident that happened, though. There were two Navy aircraft. They were just moving some missiles from one location to another. And to do that most efficiently was just to mount them on the wings of the plane, which is where they're usually carried when you're in combat, and just put them there, and they were just flying from one place to another. And the management decided, well, this was such a waste of time for them to just be sitting there and doing nothing as pilots. So they decided they would plan a test. And one pilot was told to aim at an aircraft in front, which was his friend, and fire a dummy missile. And of course, nothing should have gone wrong about this, but nobody knew that the software was designed. It was so-called smart software that even at in that age, it wasn't using AI techniques, but it was using software, which then was considered smart. It was designed to substitute a different missile if the one that was commanded to be fired wasn't in a good position. And in this case, it happened there was an antenna underneath the plane, which was right between the dummy missile and the target. So the software changed to a different target and instead fired a live one. Of course, the guy in front wondered why. This was just sort of a friendly ride for them, why the guy he'd gone out drinking beer with last night was firing a missile at him. He knows because all the bells and whistle alarms go off in the cockpit that they're being trained on by electronic device. Electronics, and he took evasive action, and so in case you're worried about him, he was able to avoid the missile. Although, you know, as soon as they got down, the Navy admirals and so on were probably one to say, how did he get away from that missile? We've got to fix it. Anyway, if you look at that, what failed? The pilot did exactly what he was supposed to do and was told to do. The software did exactly what it was designed to do. And that's what we're starting to see, or we started to see in this time, which was pretty long ago. And now we're seeing a lot. It's not individual component failures that's the problem. It's the interaction between the components themselves, in this case, or between the environment. And here's another quick example. This was an Airbus, this was a commercial flight, an Airbus A320 that was landing in Warsaw, Poland. And it's when you land a plane, the slow up, of course, you use, one of the things that's used is something called a reverse thruster, which just reverse the thrust in the wings to slow up the plane. And those are called thrust reversers, but it's very dangerous for those to come on when the plane is in the air, because if they do, then the plane loses momentum, right? And it's going to crash, it stalls. So they put it, and this had happened once, they blamed it on the pilot, probably wasn't the pilot, but it had happened before. So they, the designers of the aircraft put in protection into the software that said that don't turn on the reverse thrusters unless the plane is on the ground. But it turned out it was raining very hard. The runway was very wet. The wheels hydroplaned, and there were other factors that made the software think the plane hadn't landed. So the pilots couldn't activate the reverse thrusters and ran off the end of the runway. And this is the result after there was a fire on the plane, and you can see the actual crash. That was the actual plane itself after the incident. So that's one of the problems is, again, nothing failed. The software did exactly what it was told to do. It's just that what it was told to do wasn't correct under all conditions. And these systems today, there's just an enormous number of conditions under which they can operate, and there's a lot of assumptions, and they made an assumption here that was untrue. What's also changed is the humans' problems. In standard human factors, you look at the screen out. So human factors, people design the cockpit, they design control rooms, and they're really focused on the controls and on the screens and the displays. The hardware and software engineers concentrate on the screen in, and that used to be okay, but now it doesn't work anymore. And there's not enough attention on and no way to look at the integrated system as a whole. So what's happening is the errors and the problems, things that the humans are doing here are now related not just to the screen and the control design, but the design of the software itself. So we have things like mode confusion, situational awareness, errors of all kinds, inconsistent behavior, the software confusing the pilots and the controllers. And so we're finding brand new types of errors that occur, and we can't find them unless we look at the system as a whole. So there are these new unplanned interactions. We used to analyze the software separately from the hardware, from the operator and the human factors, but it same as what I showed you before, we now have these new unplanned interactions between the things, and we need to look at the system as a whole, integrated system as a whole. So we can't break up the system analysis problem into separate analysis anymore. So the basic problem is that the traditional safety approaches don't work very well on today's systems. They don't handle complexity that's being found in these systems. They don't handle software. They don't handle the new roles that humans are taking. They don't handle management and social systems, which are becoming more and more also more important. and they start too late. You need to design first, and humans, hardware, software, they're all treated separately. And there's no way to take, and the first thing I tried to do was take the old techniques and just extend them. And everybody tried to do that, and it just didn't work. And finally, I decided that wasn't going to work, and we needed a paradigm change. We needed a totally different way of handling these problems. It's not that people aren't trying. You know, I love this. This so hungry. I've been stuffing worms into it all day. People mean well. They're trying to do the right thing, but the problem changed, and they're no longer feeding baby birds. They're feeding human babies, and the same solutions are not going to work anymore. And the problem really is complexity. Now, there's three ways to cope with complexity. One is analytic I'll explain what that means. Analytic decomposition, statistics, you know about, and systems theory. So let me look at each of these. In analytic decomposition, which goes back to Descartes and the scientific revolution, I mean, it's been tremendously successful in science. It's really allowed modern science to exist. And what you do is you look at a system as components that interact, or you look at behavior as events that happen over time, each event leading to the other. And what you do is take each of the pieces, examine them separately, and then you combine the results of the analysis of each of the individual pieces. But there's some assumptions there that are no longer true with our systems, our very modern systems today. It assumes that the separation doesn't distort the phenomenon, that each component operates independently, there's no feedback loops, that the interactions are really fairly simple. And that's not working today because our systems with software particularly, that's no longer true. The other way of handling very complex system is to use statistics and something called probabilistic risk assessment. The problem is that you look at the probability of the failure of each of the components and then combine them. But there's assumptions under there. First of all, we're assuming that they're independent, that the failure is independent, which they aren't anymore. It doesn't work for these non-failure accidents, like the two examples I showed you of Warsaw and then the Navy planes. They're caused really by system design errors and not by component failures. So what's the probability of a system design error? Well, I don't know, especially the probability of a system design error that will lead to an accident. There are lots of design errors people can make, and they don't necessarily cause any tremendous loss. It doesn't work for software or new technology, new designs. For 40 years, I followed the reliability research, trying to get reliability assessments for software. It failed. Everybody wanted it and for good reasons, but it didn't work because software isn't stochastic. It's not random. It doesn't work for human errors. They've tried, they almost never, it's surprising because it's used so much, they've never really evaluated this scientifically. I was able to find two in the literature looking for a very long time, and both of them were abject failures, which is why nobody talks about them. They showed variance in the results of 3 to 4 orders of magnitude between different teams, calculating the risk of the exact identical system, of the same system. And there's a big difference between 10 to the minus 3 per hour versus 10 to the minus 7 per hour. The empirical results also are terrible. Every accident I've seen had a PRA that showed it couldn't happen. In fact, one of I had a phone call one day from someone they were in the UK. It was a very large global aerospace company, and they said, well, we've got this drone, this totally autonomous defense drone that does surveillance, and we bought it from a US company, and they did the calculation of the risk assessment, and it calculated that this would work correctly and not have an accident for 500,000 years, about 10 to the minus 12. And I said, well, that sounds pretty good. What do you want from me? And they said, well, we've been flying this drone for a year and it's crashed 5 times. And I said, well, that I can help you with. And we can use this and you can find where the errors are. And of course, they were mostly in the software or in the interactions between the various components. And they were able to find the reasons why these things were happening. This just doesn't work. Everybody wants a number, but unfortunately, it just doesn't work anymore. They're on these very software intensive and new, very complex systems. So the problem is that all the assumptions that were true of our systems 50 and more years ago are no longer true in the systems that we're building today. So I believe I decided we needed a paradigm change. And the paradigm change is to use something called system theory, which I'm not going to go into great detail on and don't have time to, but it's really fascinating. It actually started about in the 1920s in biology. And the goal was to find a science of complexity. And what that does when you talk about safety and apply it to safety is you change your paradigm from preventing failures or errors and treating safety as a reliability problem. And instead, you try and enforce constraints on behavior. That is, we still want to stop component failures. You could still have accidents from component failures. So we still need to do that. But we also have to enforce constraints on the interactions among the components. And therefore, what you're really doing is treating safety and other complex system qualities as a control problem. So what happens is, and I'm oversimplifying greatly here, is that in systems theory, we have a process, we have these components, they interact in direct and then also some very strange ways or unintended ways. And you've probably heard the whole thing, the whole is greater than the sum of the parts. I mean, that's really the essence of systems theory, greatly oversimplified. But what happens is there are these emergent properties that arise from the interactions between the components. And safety, security, most of the system properties we're interested in are emergent properties, right? So we can handle them with systems theory. And what do we do? Well, as I said, you would control them. You control the individual components, you control the interactions. It's a very broad sense of control. We're not saying that you put a PID controller or anything in everything. What we're talking about is that basically component failures have to be controlled somehow, and we can control them through design, and include most of the things we do now: redundancy, interlocks, fail-safe design, or through processes, or through social controls, government, insurance, law, and the courts. So we can actually add social and management into these into the analyses. And what the controllers do is they enforce constraints. The aircraft must maintain sufficient lift to remain airborne. So instead of trying to just look at every component and trying to make it highly reliable and not fail, we instead focus on these constraints, on how do we enforce these constraints. The vehicles must maintain a minimum separation. The public health system must prevent exposure of publics to contaminated water, food products, viruses like COVID, and so on. These all represent the system level requirements on the socio-technical system. And just to oversimplify again, but give the basic idea, how do you treat safety as a control problem? Well, here we have a simple feedback control loop. We've got a controller, which could be human or automation or more. This is very oversimplified. We only have one controller here, one thing being controlled. And we have a controlled process and, control actions, okay, via actuators, feedback via sensors. And we have, within the controller, if it's software, there's some kind of control algorithm. Of course, humans don't use algorithms, but there's some kind of decision-making process. But there's also in every controller, what I call it a process model, which is just a model of the state of the controlled process. You have to know what state the controlled process is in order to know what kinds of control actions are necessary. And you get that, of course, via feedback. Now, software and human-related accidents usually occur when the process model is incorrect. That's inconsistent with the real state of the process. So the software thought that the aircraft, its process model was the aircraft was on the ground when it actually, in fact, it was still in the air. I mean, I thought it was in the air. I'm sorry. The software thought the aircraft was in the air when, in fact, it was on the ground. And that captures most software errors, human errors, flawed requirements, and so on. We can handle all of them. And the analysis is basically really oversimplifying here. There are 4 types of unsafe control actions that can be given. The commands required for safety aren't given, unsafe ones are given, potentially safe ones given too late, and so on. For a continuous system, stops too soon, applied too long. And so what the analysis does, and our analysis tools, is to identify the potentially unsafe control actions using these 4 types, identify why they might be given, and then eliminate or mitigate them in the design. And if safe ones are provided, why aren't they followed? So, for example, here's the showing the Warsaw accident in that light. The hazard here is inadequate aircraft deceleration after landing. We have a pilot. We have controlling the software controller controlling the aircraft. And what happened in that case, feedback indicated the plane hadn't landed. So the process model and the software controller says the plane hasn't landed. The pilot, his process model was the plane's landed. He can see it. He can look out the window. It's on the ground, rolling along the runway. He landed it. So the pilot issues a command, a control action to turn on the reverse thrusters. The software says, I'm going to ignore that command because I'm not allowed to do that. And of course, we had the accident. That's oversimplification. But what this allows, this kind of control idea, allows us to look at software, hardware interactions, to look at human automation interactions. Here I have some more details about an aircraft. Human hardware interactions, because pilots can actually set the hardware themselves now, and even human-human interactions. So we can actually model things like the FAA's interactions with the manufacturers and the airlines. STPA is the analysis method. There's 4 steps. And define the purpose for the environment, what the system boundary is, the environment, build the models, identify the unsafe control actions, and then identify the loss scenarios. And originally we did these sort of informally, but now we've figured out how to define all of this formally. And John Thomas, a brilliant colleague of mine, has figured out now how to do. It was always a step-by-step process, but now we can give a lot more. We can really basically give like an algorithm and things to look at. And at first we thought, well, we'll automate all this. And it turned out that wasn't such a good idea. And I don't have time to explain why, because I want to leave some time for questions. But it turned out that the formal underpinning is really useful for building tools and for building new analysis methods, but it's not necessarily great to try and eliminate humans from the engineering process. This whole thing is an overall picture. At the bottom is stamped. That's just a causality model. It's a new model of the cause of accidents, and includes all the things that used the old causes, but includes these new kinds of causes. And using that theoretical basis, we can come up with all kinds of tools of accident analysis, hazard analysis, security analysis, identify leading indicators of increasing risk. We can look at organizational cultural risk analysis. We can do model-based system engineering and so on. Just to show you an example, very quick, I can't give you any of the details. First of all, I don't know any of them, and I couldn't anyway, because this is a very secret program. But 3 people, including John Thomas at MIT and a former student of mine, Bill Young at the US Air Force, and someone at BAE, applied it to a DoD program before the SolarWinds attack. And most people, because SolarWinds was a horribly effective, unfortunately, attack by, well, I guess we don't know who did it, but they were able to steal information about some of the most important defense programs for months before it was discovered. This program not just had decided to try SCPA for safety, and it was one of the few programs that was totally protected from SolarWinds. That it was never able to attack. SolarWinds never got into this program, and if you see here, we can look at the whole thing, not just at the operational support and the other things, but all at the program offices, supply chain, all these other things. And the vulnerabilities in blue are the ones that were later exploited by SolarWinds attackers that we identified beforehand and had been fixed. Give it to the credit of the people running this program that they fixed them. There were some things that we found that weren't exploited by the SolarWinds attackers, but we basically were able to find everything that they used. What's our new research? Well, the great things about this is you don't really need the details of the design. So you can start the analysis early from the very concept development, create requirements using SCPA, build an architecture, satisfy those requirements, and guide, build safety in and security and whatever other properties from the very beginning. Our latest, we have some really work by a graduate student of mine, Andrew Kopeikin, who works at Lincoln Lab on very sophisticated military systems. And we can do now sophisticated teaming between humans and automation of various sort, not just the humans controlling the automation, but really independently, the kinds of things you're all worried about. Leading into, because I mentioned new approaches to risk assurance, extension to new types of technology, machine learning. We're trying that. I can't say we're having any success. So hopefully, if we get this grant and we're successful, you'll be able to help us figure out how to apply it to machine learning and to other kinds of AI and intelligent software. And then the applicability, it turns out this works for any emergent property, mission assurance, security, as I said, serviceability, quality, producibility, any property of the system you can use this approach on. And we're just starting to look at other approaches besides safety and security. Is it practical? Well, it's been used widely. About 80% of automobile companies now use it. Aircraft and spacecraft is extensive use growing, especially defense system. These are some of the most, UAVs you know about. The GBSD is ground-based strategic deterrence. That's the new replacement for the Minuteman missile system. The Army Future Vertical Lift, this is all their helicopter programs. It's all been used on these things, and it's been used in a lot of other areas, a little bit less than this is the most extensive use. We get about 2,000 registrants from 91 countries for our virtual stamp workshops, which are basically users' meetings. And there are standards being developed, all kinds of standards that have been either created already for SDP or are being. as I said, it's been evaluated. There's lots of hundreds of evaluations now because these are really complex systems, and nobody's going to take the chance of going away from using the traditional things that everybody's always used without some convincing. And so everyone's doing parallel projects and showing the differences. Surprisingly, it's requiring fewer resources, and that's, I think, because it comes at the problem more directly. We don't have to look at all failures. We only look at the things that we know don't have to happen. Return on investment estimates are just starting, but they're looking very good. Companies don't like to talk about this. Some of them, we've invited them to speak at our user group meetings, and they say, oh, we don't want to tell people what we're doing because that's our proprietary advantage. And they don't know, everybody else in the industry is saying the exact same thing, but using STPA. If you want more information, I can send these slides, or you've got a recording of it so you can see. The book I published in 2012, Engineering a Safer World, explains all this. I wanted to try, before I published a book, I want to make sure it works. So we tried it on a lot of very complex systems before then. You can get a free download of this from MIT Press. I put it in my contract that this would be allowed. We have a handbook on STPA. It's been up on the web since 2018. Engineers in various countries have translated into other languages. It's in Japanese, Korean, and 2 forms of Chinese, and asked if we would put them up on our website, so we have them. There's been about over 400,000 downloads since 2018. And CAST is just an accident analysis method. This is after the accident. How do you identify why it occurred? And then a brand new book here up on the upper right, An Introduction to System Safety Engineering. It's a textbook because there's just nobody teaching these things. A lot of this grew up, as I said, after World War II, but in the defense systems, because they were building the most dangerous and most complex types of systems, and the ballistic missile systems after World War II. So it was all secret, and it never got into universities. Nobody. So this is not just my approach. This is all of system safety engineering. It's just, how do you do system safety engineering? It includes all the old techniques and how you design and so on, how you manage these kinds of programs, how do you analyze them, and that's it. So let me see, can I get rid of sharing? Here we go. All right, hopefully I've left a few minutes for questions.
You haven't stopped sharing, but we're happy to take the questions.
Okay, nobody question. Since I'm watching her work, I think it's a great work, so I will probably not really question. Just answer a few questions in my point. Why Nancy's statement is correct and what really happened. So Nancy's theme fundamentally is looking at interaction complexity. And there's a book called Common Accident. Nancy knows that well. So essentially, a lot of things the book predict, but the difference between the book and Nancy's work is Nancy actually provides a solution. But the book points out the risk of increasing coupling and increased interactive complexity. He warned the world, that's great. But Nancy actually done something about it. So I would say, why those problems occur? Now, if we look at system component interaction in the early days, how can you make an automobile's part in there? You go through gearbox. So the interactive complexity is a limit. If you allow a lot of gearbox, the gearbox will be too heavy for the car to drive. Now, the second era is we have point-to-point network, like in an airplane. If you put too many cables, is so heavy, even literally weighs too much fuel. So that, well, while it's inconvenient, it restricts the interaction complexity. You just cannot put too many heavy cables. Now, finally, the soil guy said, I have a solution. You can have publishing subscriber. Whoever can talk to whoever. So that causes the interactive complexity explode. All right, software are not being constrained by the historical complexity reduction, not reduction, say natural constraints, gearboxes or putting cables. Information network allows you anybody to talk to anywhere. So this really allows the explosion of unexpected complexity. So now, let's say another part. So if I see Nancy Borden saying we have broad agreement. So the question is, now we know the root cause. Essentially, uncontrolled, not properly regulated interaction allows for unexpected interaction. So let's say we drive on the intersection. There are many ways to avoid collision. You just try to figure out what to do. That's just impossible because we cannot understand how to unknown driver, their head interact. So what did we do? We said, hey man or lady, we can put a red light, traffic light. Now the traffic light greatly reduced the interactive complexity on how the cross-road driver to pass the intersection. And if you follow the line and green light, I can prove to you there will be no accident. Oh, even better, there's something called defensive driving. It said the right of way should be given up, say to safety. That means I'm on green light. I have a right of way. Some jerk just didn't stop the red light. So I said, man, if there's an accident, that guy is responsible. That's true. And take the chance. You say, no, don't take that. So now the traffic light is a Jordan simple system. We can do a lot better, but the paradigm is good. First, you try to regulate the interactive complexity. Second is you handle the violation of the protocols. That's called safety first. So rule number one is the software allows unregulated, cannot be understood because interaction goes as exponential number about components. So Nancy is very, very correct. It says that the bottom approach is no way you can get the whole coverage. So you have to go to a root cause. So one root cause is unregulated and improve the complexity interaction. So all right, okay, so what's the consequence? The consequence is you have unexpected interaction. They said that, right, the missiles define, whenever I push a button, you assume you want to or find at least any way, say a working missile and strike a target. They never expect putting a dummy on there. So what you really see is components makes assumption about environment. And the environment makes the assumption of components. And component makes assumption among each other. The incongruence of this expectation or assumptions is at the root cause. I think Nancy mentioned several times about that. So that's why I think her work is great. So, but I'm working on using simplicity, control complexity, and work on very large projects and get 10x improvement in billion-dollar projects. I won't name the project. People who know me, they know. Not convenient to talk about that. So I would now another issue. Nancy said statistical prediction is not working because they make independent assumption. Nancy is correct 100%. The question is why they make independent assumption. Can we remedy it? The reason is if you do a Bayesian statistic, there's something called the curse of dimensionality. The event A, let's say fail, condition on A, B, C, D, E, and A, B, C, D, E are highly correlated, then you cannot derive the conditional probabilities from individual components probability of fail. So the marginal, you cannot simply multiply the marginal fail probability to infer the joint conditional probability. It just won't work. Then people say, and then even worse, the problem is exponential. That's called curse of dimensional. So that fundamental mathematical thing also explains why Nancy's statement said you cannot go to bottom up. You get a marginal probability. You cannot assemble it and imply the joint conditional probability. So that is a fundamental mathematical truth. But wait, things are changing. Things are changing. There's a new kid on the block. The name is AI.
Exactly.
AI actually can compute highly coupled factors input to it. All right, the problem is at this point, AI will hallucinate. But actually, if you look at the probability of guessing, let's say a disease, actually quite high because the organs are not independent. The brain, the heart, the lung, the kidney, they're all coupled. So that's why medicine is one of the most complex because we are built into interactions. And AI actually does pretty good and it score exam. The problem is AI. Every now and then, it totally scores. So that makes it unsafe. Okay, of course, how to handle it, I think I'm not going to venture into it. So what I really try to say is Nancy's statement says the assumption independence screw things up, make the estimation incorrect, absolutely correct. But I would say with the new era of AI, it actually has a pretty high probability get the joint conditional correct. All right, so, but it sometimes totally screwed. So what should we do? I think that actually is one of the fundamental challenges. One more question I want to say is the feedback. So Nancy said, I have feedback. I say, Nancy, you are absolutely correct. But that is also makes an assumption. Let's say once you launch a missile wrong, incorrectly, you sense it. Can you take the missile back? The answer is no. So the feedback system also assumes the reversibility. All right, you can undo that. Once you launch a missile, I don't think you have any way to call it back and mang it on the wing, under the wing again. I don't think so. So even if you detect error, certain error have no way to correct. So to detect that, to make sure the feedback loop works, is you have earlier short circuit feedback. Let's say that missile said, oh, I'm going to launch. He need to have a handshake with the pilot, say, hey, I'm not going to fire that done missile, that doesn't work. I'm going to fire the one working. Do you approve it? Now, I know that is kind of slow, but you can do it automate, okay? You can, so I would say complexity reduction. Make sure when you use feedback, the event's reversible or you can arrest once it occurs. And they use Nancy's thing. I follow her work. I admire her work. I think it's great. I tell my students. But as we all know, in science, there's no such thing called last word. We can always do better. Just like Nancy has done a lot better than the traditional thing. So I would say, Nancy, thank you for giving the talk.
All right. Well, of course. And, I wish more people would take this kind of follow off on a different direction than just keep doing the same thing. You said a lot, so I'm not going to remember it all. One, of course, is that the first thing I told them, people, and everybody told them, reduce complexity. But you can't do the things they want to do by doing that. And so nobody listens. I tried that. I said, how can we reduce the complexity or redesign so that we can use the old techniques and the old approaches? It just doesn't work. You have a traffic signals is fine, but the traffic on a grid is very simple. When you have urban air mobility, when you've got all these little urban air vehicles all up in the air, all flying around, you can't have traffic signals. Now your problem is just so complex. It's not that the solution is complex, it's that the problem is complex. And there's this essential complexity. Fred Brooks wrote about this. He talked about complexity in software and systems. And he said there's added complexity, and we shouldn't be adding complexity into our solutions. But there is an essential complexity in the problems that you can't get rid of or you can't find solutions for.
Yeah,
Bayesian statistics. I promise it'll just be a minute. Bayesian statistics have been used. It doesn't work. And then the other thing is the undo, being able to call back. You can't undo, as you said, most of these things. The problem, I go to these meetings where these generals have this astoundingly complex things they're talking about. I mean, they're talking about doing things I can't imagine could ever be possible. And I say, you got to scale back the problem or your solution, because you just can't do this with today's technology, even with our techniques. And they don't want to hear that.
Nancy, you said, I agree, but I say there's something else you have not addressed. First, essential complexity, absolutely. But a lot of real system complexity is much higher than essential complexity. You agree? When you're the one you saw.
Absolutely.
Okay, now, so the step number one is complexity reduction. It's that this complexity is absolutely needed for the mission. That's the complexity. Now, you go beyond that, actually we are wrong because we don't have the capability. The second one is what you said, control. And then you do complexity control. You make sure the system stays under some boundary or sandbox. If you know the complexity cannot be reduced, and you do not, and that complexity can compute, the complexity might create unexpected interaction that lead to catastrophe. Then you have a choice to make. Number one is, I take the chance. A better way is, can we control the complexity? Can we limit the behavior through capability control, through interaction control? In some sense, is complexity control. Okay, so I think we are largely agreed. I recommend all the students read Nancy's thing. So since I'm working in the area,
I mean, this is why we want to do things early. If you, at the conceptual design, you can understand the scenarios, then you can reduce unnecessary complexity.
Absolutely, I agree.
But you have to do it at conceptual design, and you need some way of finding out what is essential and what isn't essential. It's not so simple. So there need to be engineering tools to figure out how to get rid of non-essential complexity, and still we want to achieve our goals.
I agree.
Louis, thank you for active discussion and all the inputs. I think Nancy has a schedule today. I don't know if we can take one or two more questions, because I know Nancy is in an ONR meeting formally today. Let's see.
That's fine. If you want to stay, I mean, it's over. I think your scheduled time, but I'm happy to. I'm free for.
We'll take a few more questions. Let's see if we have more questions from the audience. Who has questions?
I think I've confused everyone.
No, thank you very much for the talk. No, it seems nobody else is coming up with a question, or maybe I mentioned that you are in a meeting. So I don't know, Louis, do you want to wrap up, or So the call is recorded and people will watch. That's what we get. That's where we get subsequent questions once we post the
I
call.
would say Nancy's great. Invite her again. Go a little bit deeper. She has a lot, actually, very powerful tools. Actually useful to urban mobility.
Mhm.
So invite her again. Say,
Okay. Yeah, we've been
2.0.
we've been working on the urban air mobility for NASA for several years, and you know the complexity of that, the difficulty of that. They're going to have to add rules. You cannot have complete chaos up in the skies, have everyone go everywhere they want, and somehow the computers on the planes are going to keep self-separation between this. It's just not feasible to build those things. But we can have urban air mobility, but as you say, we're going to have to limit. We have to figure out where is the limit of the complexity that we can handle today.
I agree.
Stretch it. I mean, hopefully in the future.
We conceptualized that before. So in urban mobility, what are the essential complexity, or roughly, let's say, what are the, roughly, let's say, the bound on the essential complexity we cannot reduce? So I say urban mobility essentially is a very, very big challenge, and to apply all what you said, this is a great guinea pig. I will invite Nancy said, let's take a look at how to make sure the only essential or as approximately essential complexity are remained, and how we constrain the fail mode through behavior control. Okay, so I would say let's invite. She is really the leading expert on complex system safety, and people like Nancy love a challenge. She doesn't work on old problem. And I know sometimes she talks to people and simplify things, just make sure the world can benefit from her research. But I know people like her heart is taking on the complexity problem. And see if she can really early conceptualize it, do something about it. I say, hey, Nancy, take on the challenge. Come back and say, how do we apply your tools? Just high level.
We have, I have a student, Justin Poe, who's just finishing his dissertation on urban air mobility. He's looking at the whole traffic control, trying to avoid collisions. And, you know, we've handled air traffic control by simplifying the problem very much by having a centralized control. But what we do now in air traffic control is limit what people can do. So they can't go point to point. They have to doglegs. They have to simplify it, basically the problem of trying to prevent collisions by keeping them far away. That won't happen in urban air mobility. And the first thing people said, well, we'll just let computers on the planes and everybody will self-separate. We won't have any of the central control. And that's not going to work either. So what he's trying to do is, how do we design these? How do we assign functions to the central computers, to the individual computers? How do we stretch the lack of control, not lack of control, the freedom of these things to move where they want, as much as possible while still preventing collisions. And it's a really complicated problem. He's doing a very interesting dissertation on this. What architectures basically?
Yeah, I would say, well, why don't we look at that together? All right, that's one thing. Another aspect is the complexity being introduced by something called AI, perception. There's no classical way of doing perception. And perception is crucial. For example, NASA asked to do safely a perception guide landing on a small airport without all the fancy guidance system or guiding slope or something like that. So now the self-driving car is unstoppable momentum, like it or not. And perception safety, the complexity between an AI perception system and a control, which we understand much better. That coupling is the safety research challenge of the moment. Okay. All right. So we have a lot of things to work on. I just say, Nancy, you are great. You are a great team.
Oh, thank you.
Why don't you work together?
So we have one more question, Louis. Let's see if people can ask another question. Thank you, Nancy. Thank you for staying long. Okay.
Well,
Go
thank
ahead,
you.
Sandy.
I think this will be
Hi.
great fun if we get this Navy grant, because this is what everybody wants. The autonomous cars are using lots of machine learning, but how do we get safety out? And they use SDPA, but we haven't figured out how to deal with this. So it's really an important problem to work on.
Sandeep, go ahead with the question.
Yeah. Hi, Professor Nancy. Thanks a lot for the talk. And, we tried to do this STPA on this robotic example, and John gave a lot of feedback that was fantastic. But one question which I found is, so when we were doing STPA, we were determining these hazards and losses. And John pointed out that, this is not really an hazard and so on. So it led me to think that, especially in the AI-based systems, I might not be able to accurately say what the hazards are. And let's say I'm not able to determine those unsafe states, right? Which is what the hazards clearly identify. And I did the STPA and somehow I deployed it. Now something went wrong. Can I determine what actually led that issue or that loss which occurred? Because I did not identify the hazard. So is there a way that I can reiterate and figure out, especially in AI-based system where, these unsafe states are very hard to find?
Well, yeah, I don't know about AI systems. The losses have to be defined by the stakeholders. That's not the engineer's job to determine what are important losses. That's somebody else's problem. Once you get the losses, you define the system hazards, which is fairly straightforward. The problem is refining those system hazards, right? So that the hazards and identifying them with the interactions of the components and the hazards of the individual component behavior. And that's what SDPA is meant to do. It's not easy. John has recently just started talking in the last month about his new method for finding scenarios. That's how you find the hazardous behaviors. Look at the scenarios that can lead to it. And that's been the hardest part. And we haven't been able to help people with it. We just say you have to think hard about it.
Yeah,
that's not satisfying. But he now has a step-by-step process for identifying these, which I think is going to help a lot. I mean, this is all new, and we need to keep developing. We haven't solved all the problems yet. We're just starting on helping people get going on the problems. Now we need to extend these things, this approach, and figure out new and better ways to do it.
Okay, yeah, that might be really helpful. And in general, I think the larger question for me would be STPA can be as good as the humans who are actually accounting these hazards, right? Once it goes beyond that's the challenging part.
Well, it definitely is. And that's why, as I say, we can actually generate the unsafe control actions automatically. We have been. That was John's dissertation. We can generate all of those. We get too many, and a human has to come in and say, because the computer doesn't know what's physically possible. So the computer, can say, well, just drive away at 1,000 miles an hour. Well, that's not possible.
Right.
So a human has to come in and do that. Now that we've got more automation or a step-by-step process for doing the scenario, I think that's going to make a big difference. And at first we thought our goal was to automate all this stuff. Of course, I'm a computer scientist, so the first thing we do is think automate. And what we discovered is that it isn't so good automating. The humans think of things beyond the algorithms. Humans are so flexible and so adaptable that our goal shouldn't be replace engineers.
Absolutely.
We're not going to replace engineers. We need humans, and that's good for all of us, so that I don't have to worry too much about a future job, but all you young people don't want to be replaced by computers and have engineering done by computers, and it won't be. That's the good news.
Okay,
Thank
perfect.
you, Nancy.
Thanks a lot.
Cynthia, I cannot say it would definitely work. But here's what I would do, because I'm working on AI reliability safety. The first thing is the reachable target of your AI, who it can influence. Can you have any control? He said, no, I don't know how the output will go to whom. I said, then you are at loss. The problem is gone. First thing is you want to regulate who can talk, who this AI might talk to. Number two, okay, so you get the list, suppose it's manageable. Second thing is that, what is the worst case impact? Okay, start from there.
Yes.
Yep. Perfect.
And then there's a lot more you can do. If you're interested in more, talk to me offline.
I think that, the problem is that the computer scientists are sort of used to looking within, and they want to fix the machine learning itself. I think we have to start thinking more systems. And what we're going to have to do, we're not going to fix the computer machine learning, I don't think, but we can build a system around it that will allow to us to safely use machine learning. But it's not the way people normally think.
Yeah, actually, there's a name for that system you talk about. It's called simplex architecture. Its job is to contain the behavior of a software who might have arbitrary bugs. Look it up.
If you can do it, that's great.
Well, it has been done.
Good.
It has been done and being used. It has great result.
Thank you. I think we have a great discussion here, but I want to kind of make sure we don't delay Nancy too much from her other meetings and daily schedule. Unless there are some other questions, we could take quick questions. If not, Nancy, I will have to ask you to email me the slides that you just now presented, so we post it along with this video, right?
I'll send them
We'll
right
post
away.
the video, right? Louis, are you done? Can we close the Teams? If no more questions.
I invite her again. I haven't heard your invitation again. Because inviting people like Nancy, it allows us to do a better job. No any individual for complex systems, no any single individual can really have a total solution. So we all need to work together closely. And the urban mobility complexity control actually needs Nancy's thinking. Let's invite her back. I don't know if she is willing to take on that challenge because we cannot pay her. We are not like a Navy. Say, hey, Nancy, we give you a grant. No, we cannot do that. So it's really sad, Nancy, do you want to take that challenge?
Sure. Thank you, Louis. Thank you for your guidance, and happy to work with all of you.